All right, hello, Winnow students. Let me try to answer this question. As you know, we're in Chapter 8, and I got a question about number 23, and it has to do with rotation. We're doing rotational mechanics here. And let me just read number 23 here. It says, a solid sphere and a solid cylinder are made of the same material. Well, for this, let me grab my little baseball model here. So this will be my sphere, and I guess it is kind of solid. It's got foam all the way through it. It's not very heavy, but this will be my sphere. And I was looking around for a cylinder, and I found this top off of a cleaning can. So it's not solid, but let's pretend it's solid. But I like the fact that they were about the same size, and you know the I guess would be the height of the cylinder, or the length of the cylinder is about the diameter of the ball here, and of course the diameter of the cylinder here is about the diameter of the ball. So these will be my two. So this will be the solid cylinder, and this one here will be the solid sphere, and this will be the solid cylinder. Okay. So pretend they're solid and pretend they're made out of the same material. It says if they have the same mass and the same radius, which one has the smaller rotational inertia about its center and why? Okay, so the lesson here for this chapter was if you have something that's rotating, and so maybe I'll make this the axis of rotation, and maybe I just have a little point mass out here. And so it's some distance r out, and it's some mass m. And we make it rotate. We would say that as an analogy to mass being the inertia and the resistance to translational motion, we have this similar effect, which we labeled as I, and we called it the rotational inertia. It's also often referred to as the rotational moment, or sometimes the second moment. And the reason it's called the second moment is the way you would calculate it is you would take its inertia, and then you would say, well, how far is it from the rotational axis squared? And so that's a math symbol. When you take a quantity, inertia, and you multiply it by a distance raised to whatever power, that is the first moment or second moment or third moment. So we're raising to a power of 2, so this would be a second moment in terms of math. A first moment would be like this, a second moment would be like this, and a third moment would be like this, and so forth and so on. So whether you want to call it rotational inertia, which I like for this class because we tend to be more conceptual than mathematical, or whether you want to call it the moment of inertia, since physics people and engineering people, the first moment has to do with center of mass, not inertia. We just call it the moment of inertia. But I guess technically it should probably be referred to as the second moment of inertia. That way it would have its math name as well as the physical meaning. But like I said, I like the rotational inertia because what it is an indication of how difficult it is to get something to rotate. Or for that matter, if it's already rotating, how difficult it is to get it to stop rotating. So you can see that if I had this little point mass here, the bigger the r is, the harder it is to get this thing to rotate. Or if it's already rotating, the harder it is to stop it from rotating. So, and it goes like r squared. Now, here's where it gets more complicated, and so a problem like this, where you had, say, a sphere, you would have this rotational axis, and if you let me just do a cross-section, it looks something like this, and you go to make it rotate, well, some of the mass, I'll just maybe grab a color here, some of the mass is actually really close to the rotational axis. So I'll put like a bunch of little chunks of mass kind of along the vertical diameter of this sphere that are kind of close, and so those would be easy to get to rotate. The ones that would be hard to get to rotate are the ones out here. They would be what you might call along the equator of this sphere, and so these things. But notice then that over here near the top, you might call this the poles of the sphere, that you really don't go out very far with the mass because of the curvature of it. See, and that's what makes it different from a cylinder. So if I look at a cylinder here and say, okay, here's the rotation of the cylinder, and I do a cross-section, I'll maybe even try to give it a little bit of 3 dimensions, so it's more than a cross-section. And you go to rotate it, like the sphere up here, you do have a bunch of mass that is fairly close to the rotational axis. So those would be easy to spin, and these would be one and the same. But it's this stuff out here that would be hard to rotate. And for the cylinder, there's a lot more mass out here where it's hard to get it to rotate than for the sphere. For the sphere, it's just at the equator. But for the cylinder, it's all the way from the top of the cylinder to the bottom of the cylinder. So this one's going to be much harder. And I think the question, let me go back to the question, says which one was easier. It says, let me read it here. It says, if they have the same radius, that was important. Okay, so we're comparing the same distances. Which one has the smaller rotational inertia? And so it's got to be this sphere. The sphere, as you kind of look at it, really, even though we say it has a radius, the mass that is at the radius is only the stuff near the equator. The stuff near the poles doesn't go out nearly as far, whereas the cylinder, all the stuff goes out the distance of what would be the same distance as the equator on the sphere. All right. Hope that was helpful.